So G will be a semi-simple Lie group, simple Lie group. All the time semi-simple, but sometimes when the statement is not correct, then simple. And K a maximal compact subgroup, so there is unique. So this is non-compact simple Lie group connected. The example to have in mind, I always like to think about two examples. One is SLN R, and the other is SON1. So here so there are many more examples. Sometimes you want a specific Lie group, but this two represents, say, high rank. The rank of this one is n minus 1, and the rank of this one is 1. So that's the rank. So then there is some dichotomy between high rank and rank 1. This is sometimes we think of it as hyperbolic, and this as more rigid. K is a compact, and then X will be G mod K is the symmetric space. So the symmetric space of this one is the hyperbolic space of dimension n. And so this is a nice, very nice, simply connected, contractible Riemannian manifold of non-positive curvature. In this case, even negative curvature, and in that case, non-positive sectional curvature. And now, G acts on this space by isometries. And actually, G is almost the isometry group of that space. So in a sense, to investigate this creature is the same as investigating this creature, Riemannian symmetric space of non-compact type. And if gamma in G is discrete subgroup, then gamma corresponds to a manifold, or more generally, an orbifold, which is the quotient G mod K mod gamma. And so this is the orbifold associated to gamma. It's a manifold if gamma is torsion free. If there are no element of finite order, then it's a manifold. And if in general there are some ramified points, almost everywhere it looks like a manifold, but there could be some. And then there is a Haar measure on G corresponding to Riemannian Haar measure on G corresponds to the Riemannian measure on X. And this gives you, so there is a volume form, and you know the manifold of the X mod gamma, and the volume of M, which is also, if you normalize properly, it's also the co-volume of gamma inside G. And if this volume is finite, then gamma is called a lattice. So G mod gamma is a manifold of, is a space of finite measure. Sometimes we normalize it to be 1. And okay, and then there is the theory of lattices is maybe one of the most beautiful theories in mathematics. It's very thoroughly investigated in the last 60 years. There is a wonderful aspects of this theory from geometric group theory, dynamical number theory, and etc. And okay, much less is known about discrete subgroups which are not lattices. So, for instance, subgroup of infinite index inside lattices. So while we understand very, very well, also there are also many open questions, but we know a lot about lattices. We know today almost nothing about about what we call thin groups, like discrete subgroup of infinite covolume. Okay, so what I will discuss in this two lectures is a probabilistic method, a random approach to say things about lattices, and also in the last lecture about non-lattices, but discrete subgroup in general. We denote by sub G the space of a closed subgroup of G, and there is a natural topology which makes it a compact metric space. It's called Chabuti topology. So there is a topology. Maybe the fastest way to define it is to say that the distance between two groups is the integral of the house of distance between the intersection of H1 with the ball of radius R around the identity in G, and the intersection of H2 with the same ball. And then you need to multiply by some function that decay fast enough so that this will this integral will converge, and this tells you the distance between two groups. So basically, two groups are close to each other if, when you look on a large ball in G, they're very close as sets in the house of distance. So that's a metric, and then this space sub G is compact. So this is quite general. Whenever G is a locally compact group, you can define this space, and this will be a compact metrizable space. And one thing to say about this space, one thing we want to observe is that G is an isolated point. So basically, it's a complicated space. So it's always compact, but it's a huge space. So it's very hard to say things about it. And you can use it for many things. For instance, if you look at the group gamma, take gamma to be SL3Z and consider the conjugacy class of SL3Z, you get some subset here, and then you take the closure. Then you get a compactification of this space of G mod gamma. In that case, it will be the Borel cell compactification. In general, it's a very complicated compact space which carries a lot of information. And since it carries so much information, it's hard to use it directly. So instead, what we do, we consider measures on this space. So I'll do it in a moment. But first, let's see one result that is useful for position. G is isolated. You cannot approximate the group G itself by proper subgroups. So this is not true for any local. For instance, if you consider R, the group R, you can approximate it by cyclic copies of Z with so every proper closed subgroup of R is either trivial or discrete, cyclic, and if you take it with period alpha, when alpha is very small, you can approximate R by discrete subgroups. In a sense, okay, for R, this space sub G is simple. It's actually an interval, a closed interval, so there's no isolated point. But in general, it's a complicated space, and if G is suppose if G is a compact simple group, then for instance, there is a theorem of Jordan that tell you that finite subgroups are basically virtually like they're abelian, almost abelian in a uniform way. So in a sense, so if G is non-abelian, in our case, it's not compact also. You cannot approximate it by proper subgroups. Basically, this is true more generally whenever G has no abelianization. Whenever so this is for Lie group, this is if and only if the commutator is dense in G. It's also true for a non-Archimedean Lie group like SL on QP. So maybe I'll leave it for the exercise sessions to discuss it, but it's a good remark to note that you cannot, and this was known since the 50s, so this is known long ago. It's a good remark because then we can just remove this point, ignore it, because we and it's good that we will not get there if we take some process on sub G. You want to analyze the limit, so at least this point we can avoid. We'll come back to that. Anyhow, so can I hide this for a moment? So suppose okay, so what is a random subgroup? So definition by random subgroup is a probability measure on sub G. So we have any probability measure on sub G is a random subgroup. Let's also say inside sub G you have a subset. This is the discrete subgroup, and so this here is another exercise for you. This subset is open. So it's a nice subset inside G. This is basically equivalent to the fact that G is a Lie group. You know, this Hilbert fifth problem that to say that a locally compact group is a Lie group. It's if and only if it doesn't have a no small subgroup. There is an open subset, open neighborhood of identity that contains no non-trivial subgroup.
What does this Lie group mean, like real Lie group or like?
Yeah, real Lie group. So yeah, this is a equivalent. Yeah, for SLN-QP, it's not true. The discrete subgroup is not open anymore. You can approximate the trivial group. So this statement, I think, it's equivalent to the fact that G is a Lie group.
Sorry, all the subgroups are themselves discrete. They're not sitting discretely in the Chaboti. Okay. Yeah. Inside
the Chaboti topology, the set of discrete subgroup is an open set. Yeah. So this is because G is a Lie group. It's not true for general. This fact is true also for p-adic, non-Archimedean, or positive characteristic Lie groups, but here it's for a real Lie group. And then so by a discrete random subgroup, a discrete random subgroup, and most of the time this is what we care about, is a measure mu is such mu which whose support is this. Okay, the support is closed, but you want mu of the probability one, you get a discrete group. So that's a discrete random subgroup. Okay. So now G acts on sub G by conjugation. Okay. And then a probability measure which is invariant under this action is what we call an IRS. an IRS invariant random subgroup is a G invariant probability measure on sub G. So basically, and so an IRS became quite popular in the last 12, 13 years. So many people got interested in studying invariant random subgroups. Surprisingly, there are a lot of applications. We will see some, and basically in the first two talks, so today and tomorrow, I will concentrate on IRSs. But for me, only in the setup of simple group, semi-simple group, because this is what I mostly care of. And in the last talk, we'll discuss non-invariant random subgroups, which is a notion that was less investigated. It's much more general. So in a sense, so it is a bit surprising that IRS became so successful, because in the context of groups, semi-simple groups, these are non-amenable group. If you restrict yourself to only to invariant measures on this compact set, then you lose a lot of information. Non-amenable group is a very few such actions. I mean, much less than general action. But still, it's quite good. We will see that it's quite good notion. And so, if you want, let's observe that IRS G, the space of all IRS, probability measure on sub G. We can write it in the following, which are invariant under the G action by conjugation. And this is a compact space. Is a compact space with respect to the weak star topology. There's always when we consider measures on measures on Hausdorff compact space, we take them with the weak star topologies. A sequence of measures converge to a limit, or a net of measures converge to a limit if the integral of every continuous function converge to a limit. So that's so basic example. So first example we have in mind is a normal subgroup. So that's for general locally compact group. Normal subgroups corresponds to Dirac measure. So a measure that's supported one point on one group and it's invariant under conjugation must be a normal subgroup. And the second basic example is, do you see when I write here or not? It's not hiding. So the second is lattices. So let me explain. So if gamma is a lattice, then G mod gamma is finite volume, which we can normalize to be 1. You can still consider the probability measure. So yeah, so suppose that gamma inside G is a lattice, so that's my short notation for saying that the gamma is a lattice in G. Then let mu be the probability measure on G mod gamma. So by Hart theorem or by the extension of Hart theorem, there is a unique probability measure on G mod gamma. We call it mu. And now consider the map. There is a map from G mod gamma to sub G, sending a coset to the conjugate G gamma G inverse. And if you put the push forward of mu, of mu under that map gives an IRS which we denote by mu gamma. So mu gamma is the same as mu of delta if delta is the conjugate of gamma. So it's actually an IRS that corresponds to the conjugacy class of gamma, and its support is the closure of the conjugacy class of gamma. So you see every lattice correspond to an IRS. So we see an IRS is a generalization both of normal subgroup and of lattices. So it's already say that it's something interesting because any theorem that you prove for IRSs, it will apply to normal subgroup and to lattices. And once you see that it's generalized lattices, then one thing to say is now we have a lot of things to do. We have a lot of theorems about lattices. Let's try to generalize them to IRSs. So and people do that, and it's good because then we understand IRS better. But another direction is to say, okay, it's a generalization of lattices. Let's see if we can say a new thing about this creature and deduce new results about lattices, and that also works, surprisingly. So we will see some examples. And indeed there are a lot more IRSs than lattices, but maybe before discussing that, let me give another way to think about this random conjugate of the lattice. So here is something you can do with this observation. So consider say a hyperbolic surface, a closed hyperbolic surface, say something with picture like that, and so it has a hyperbolic metric. And then if you picking a random point and or if you want a random point and a frame, so in that since it's two dimension, so we pick a random point and a unit vector. Once you do that, it gives you can embed it gives you a way to embed a fundamental group, the surface group, inside the SL2R, which is the group of PSL2R, which is the group of isometries of the universal cover. So any choice of a point and a frame, a point and of a unit tangent bundle, a unit tangent vector, gives you some conjugate of the fundamental group inside SL2R. And if you take a probability measure here, it gives you a probability measure on all the conjugate. So it actually gives you an IRS. So in a sense, the Riemannian metric, the hyperbolic metric, will correspond to an IRS. And any compact hyperbolic surface corresponds to an IRS in SL2R or PSL2R, doesn't matter. And now we know that there are many different. There is like 6G minus 6 dimension. There are a lot of Riemannian structure. Each of them give me an IRS. Now we go back here and remind ourselves that the space of all IRS is a compact space. So we can take a compactification of all this creature. And this gives us a compactification of the Teichmüller space or the moduli space. So by looking at IRS, we get some new compactification of okay, this was investigated by Yannick Krivka. He analyzed this compactification. It's very close to the well-known Deligne-Manfred compactification. This is just a remark. Let me say another classical. So what I'll do in the remaining time today, I will demonstrate why I want to demonstrate why looking at IRS gives new things about this about lattices. Yeah, so let's start by extending well-known results about lattices to IRSs. So one of the classical theorems about lattices is the Borel density theorem. So when we think about lattices, the philosophy that I like to think is that lattices are a discrete approximation of G. So in a sense, if gamma is a lattice in G, then they resemble each other. So for instance, in general, if G is amenable, if and only if gamma is amenable, G has property T, if and only if gamma has property T, and so on. But more general, there are a lot of results of this direction. One of them, the algebraic, is the Borel density theorem. So if you have a simple Lie group and gamma is a lattice in G, then gamma is a Ricci dense. Any polynomial equation that is satisfied on gamma must be satisfied on G. So in some sense, that's similar in algebraic sense. So this also goes to IRSs, the same result, and one of the consequences of Borel density, one of the first consequences, if you read a basic book about lattices, like Raghunathan's book, one of the basic consequences that if you have a subgroup of finite covolume, it must be discrete. So in G, if you have, let's say, SLN R, and you consider a subgroup of finite covolume, H is a subgroup such that G mod H has finite volume, is finite probability measure, which is G invariant, then H must be discrete, must be a lattice. So this is one of the consequences of Borel density. And this result applies also to IRSs. So here is the theorem. Let me call it Borel density theorem for IRSs. So let's let G be a simple group, and anything can be generalized to semi-simple, but then you need to be a bit more careful. A simple Lie group, non-compact, simple non-compact Lie group, and mu and IRS. Okay, so two things. So first, mu is with probability 1. So if mu of the trivial group is 0, so there is no atom in the trivial group, then almost surely mu almost surely we have the Ricci density. How should I write it? Then then mu is supported on the Ricci dense. So so of course one is a normal subgroup. You can have the trivial IRS, but otherwise anything in the support is a Ricci dense. And 2, if mu of the group G itself is 0, then almost surely you are discrete. Then mu of sub discrete G is 1, i.e. almost surely discreteness. So this is the Borel density theorem. It's a theorem about lattices that generalize automatically, almost automatically, to IRS. So I say almost automatically because the first proof of Borel density theorem, the proof by Borel, which is also it's a beautiful proof. It's written nicely in Raghunathan's book. But a year after Borel gave this proof, Furstenberg gave I would say a much better proof. I mean, it's not true that it doesn't recover the full generality of Borel density, but it recovers it for lattices, and it's really much easier to understand and to generalize. So Furstenberg, what is Furstenberg proof or Furstenberg lemma? Let me recall that, let's say, again, G is a simple, I don't need to write it any time, all the time. G is a simple, connected, non-compact Lie group. And let's say that if rho is an irreducible or is it from G is a representation of G in GLN, GLN, let's say R. If rho is an irreducible representation, so in particular the image of G is non-compact. Because yeah, G is a simple group with some. Then there is no G invariant measure on the projective space P n minus 1 R. You cannot have G invariant measure probability measure. There's no G invariant probability measure on the projective space. So of course, there's the Furstenberg lemma is more general, but the idea that I'll tell you is the same, and the idea is yeah, you don't need G to be simple group. Any irreducible non-compact subgroup of GL and R does not admit invariant probability measure on the projective space. And the idea is to look at the K decomposition of GL and R, the Cartan K decomposition, where K is just SO and R, the maximal compact, and A is the diagonal. A plus is A1, AN is this group, that AI is at least AI plus 1, and so that's a semi-group, and there is you can write G as K A plus K, right? You're familiar. So there's in the theory of Lie group there's like a list of 5 or 6 standard decomposition. One of them is the K decomposition, which we should always have in mind. So every matrix you can write as orthogonal matrix times diagonal matrix times orthogonal matrix, and this diagonal matrix is unique. This composition is not, it's almost unique, but not unique, but the non-uniqueness is in the compact, not in the middle, not in, but it doesn't matter. So now from the K decomposition, you can deduce that, because if Gn are element in GLN R that goes to infinity, basically the matrix norm goes to infinity, it means the only way to go to infinity is in the A part. because K is compact. Then up to taking subsequence, we have that there is I between n minus 1 and 1, such that AI of Gn divided by AI plus 1 of Gn goes to infinity. There must be a jump somewhere here in the middle. AI plus 1, the ratio between them, because the product of the AI is 1. So we are not in GLN, we are in SL. Sorry. Yeah. So the product is 1, and therefore there must be a jump. If you go to infinity, then A1 go to infinity. By the way, A1 is the norm of G. So A1 go to infinity, but the product is 1, then there must be a jump somewhere that goes to infinity. But what does it mean, this jump? It means that if you look at this, how G acts on the projective space, it takes almost all the, like there is a n minus I dimensional subspace that if you are not very close to it, this element G takes you to this I dimensional subspace. Okay, this K and K may rotate them, but you don't care where they are. So there is, so you see that the measure must be since this element preserve the measure must be inside some proper subspace, supported in the proper subspace. Now, since the action is irreducible, that cannot happen. So this is I hand wave, because if I would write a formal proof, it will take half an hour, and I only have an hour and a half. So, yeah, okay, so I hand wave, but you can look it up. It's written in many places. Basically, the K decomposition tell us that this observation of Fürstenberg, that there is no invariant probability measure on projective space under non-compact irreducible subgroups, and from this we deduce the following. So we deduce that because this implies the Borel density theorem, because so this will be part A and this will be part B. So now we can deduce A and B by considering for part A, considering let's say for A, the connected component of the Zariski closure of gamma. If you take it, and for part B, let me just write it and then explain what the connected component of gamma. Yeah, I pick a random subgroup. I don't know that it's discrete, and I don't know that it's Zariski dense. But to prove that it's Zariski dense, I look at its Zariski closure and take connected component, and then you see you get or if you want, not that, but the Lie algebra. Also, the Lie algebra. I have a random subgroup. I take its Zariski closure, take its Lie algebra. I get probability measure on Lie algebras, which is invariant under G. Fürstenberg lemma tells us that's not possible. Okay, there is a short way from Fürstenberg to that. You need to Fürstenberg, I told you, for projective space. Now it's not projective space; it's Lie algebra, but then you can take the wedge product representation to exterior power representation of the right dimension, so that this Lie algebra become one-dimensional. I mean, if the Lie algebra is k-dimensional, you take the k exterior power, you get another representation and then you get a measure on the projective space. And maybe you should recall that every it's a semi-simple Lie group, it's completely reducible. Every representation is a direct sum of irreducible one. And once you remember this fact, then from Fürstenberg lemma you deduce that there is no measure on the set of Lie algebra or Lie subalgebras, which is maybe I just write it as a lemma. There is no probability measure on Lie subalgebras of G, which is G invariant, except beside the Dirac measure on the trivial Lie algebra, the zero, and the Dirac measure on the full Lie algebra. Okay. Besides Dirac measure on the zero Lie algebra or the full Lie algebra. If you have a simple, if you have, there is no, which is G invariant, but you can replace G by any, you can replace G by GLN, and the invariants you just need under non-compact irreducible subgroup. And from that, since there are no measure, you cannot choose randomly algebra. You cannot choose invariantly randomly algebra except if you choose the trivial or the full algebra.
So this follows from the Fürstenberg lemma?
Yeah, that's the consequence of the Fürstenberg lemma.
Because the Fürstenberg lemma was not only true for simple group, it was true for any group, right? And now we need simple. So
I use G both for GLN and for the subgroup. So formally, if you want to say precisely, more generally, take if you want G. In the statement, there is no. If you look at all Lie algebras of GLN, there is no probability measure on this set of Lie algebra, the space of Lie algebras, which is invariant under H whenever H is an irreducible non-compact subgroup.
SLN, right?
SLN. Probably GLN is also. Yeah, in GLN you have center. Yeah. Yes. So, but yeah, you can replace the big group by any simple Lie group and the small group by any non-compact irreducible subgroup. Anyhow, once you apply to the Zariski closure, you get Zariski density, and once you apply to the standard closure, since gamma is closed, it's a invariant, then you get discreteness. Okay. Let me just tell you now one nice consequence for lattices from this. So the first corollary that we see, so since G is an isolated point, we see that now that any invariant random subgroup is supported on discrete subgroups. Any invariant random subgroup without atom at the full group must be supported on discrete subgroups. So that's a nice corollary. The set of discrete IRS is compact. If G is a simple Lie group, the set of discrete IRS, which I denote by IRS, dg is compact. And why? Because, yeah, if you want any IRS by the Borel density is of the form mu equals some alpha times Dirac at G plus 1 minus alpha times mu d, where this is discrete. Any IRS of this form is of this form. So if you consider only so the space of all mu such that alpha is 0, so all the support is of discrete, is still compact. The limit of such must be also like that, because G is an isolated point. G is an isolated point, and if any point in the support, if it's not G, it must be discrete. It means that the set of all discrete IRS is compact. Now, this observation, right, so it's not so deep, but it already gives something wonderful, which is the Kashdan-Margulis theorem. So, what is Kashdan-Margulis theorem? And this will be I think a nice way to finish the first lecture with some application. So Kashdan and Margulis proved that suppose if you care only about three-dimensional hyperbolic manifolds, there is a lower bound for the volume. The volume cannot be arbitrarily small. Similarly for surfaces, hyperbolic surfaces, that was known before by Gauss-Bonnet theorem, but if you take any symmetric space and consider only manifolds which are locally isometric to that, there is a lower bound on the volume. So what is the Kashdan-Margulis theorem? There is a lower bound, so there is given G, there is let's say some delta bigger than 0, such that the core volume of gamma is bigger than delta for any lattice in G. There is a lower bound on the core volume of gamma of lattices, or lower bound on the volume of manifold of the form G mod K mod gamma. So that's a beautiful theorem. It's a starting point of many other things, like then, yeah. But for instance, in dimension 3, there is a lot of investigation of finding the lattice of smallest covolume and etc. Also for other groups, but and anyhow, why this follow from what we just said? So I claim that this is so here is the proof.
Is this always achieved, like this infimum?
Sorry?
Is this infimum always?
Yeah, this infimum always achieved. Yeah, this but that's not that's separate. It's always achieved, but and sometimes in co-compact lattices, sometimes in not co-compact. So it's and in many cases it's not known what is the minimum, but it's always achieved. And here is the proof using IRSs. I actually write a more general claim. Sometimes when we can write a more general claim, it becomes easier, right? So here's a more general claim, proposition or theorem. There is an identity neighborhood U of G. Yeah. So it is subset of V, such that for any discrete IRS mu, the probability that a random subgroup intersect U non-trivially is smaller than half. Yes, it's smaller than half. So with probability at least half, so there is some fixed U independently of mu. It's good for all mu, such that for some fixed identity neighborhood, such that for every IRS, the probability that I intersect this IRS, that they intersect U non-trivially, cannot be bigger than half. And what is the proof? So I have only 2 minutes, so I'll write the proof in 2 lines, and maybe tomorrow I'll say a bit more about the proof, but basically I think these two lines can convince you. So suppose the contrary. Suppose the contrary, then let UN be ascending neighborhoods converging to the identity. So we look inside G and we look at smaller and smaller neighborhoods such that the intersection is just the identity.
Descending.
Descending neighborhoods converging to the identity. So U1, U2, U3, and so on. Suppose they're relatively compact and converge to the identity. Assuming the contrary, let mu n be such that, so be an IRS, such that mu n of this with un is at least half. So it's counter. This is the counter example to the statement that we want to prove with respect to un. That's mu n. By compactness, mu n, if you want k subgroup, converge to mu, a discrete IRS, some discrete IRS. Now mu has this property with every open subgroup. This implies that mu is not discrete. So this contradicts compactness. By contrast to compactness. You see, mu is not discrete. It cannot be supported on discrete subgroup because it intersects every non-trivial subset of every non-trivial. Okay. End of time. But you can ask about this, or tomorrow I can give more details about that.
This is a detailed proof, right?
Sorry?
I mean, what details are missing? Otherwise, maybe you will not be
no, I should explain why a limit is not discrete. You can say, okay.